So yeah, first of all, welcome everyone to the Subsurface Systems Modeling webinar organized by the EAGE Technical Community called Basin and Petroleum Systems Analysis. Today our special guest is Balazs Badics, and he will talk about basin modeling in oil and gas, so more like a traditional topic. Yeah, that's we are excited because getting contributions directly from operators is not easy. Oops, how do I advance?
Page down.
Try that. Yeah. So today's agenda, it's just a quick introduction by myself, then the main contribution from Balazs, and then we're having a Q&A session later on. In terms of your questions, the best way is to type your questions into the little chat functionality of this WebEx tool. So on your lower right, there should be a chat button, and if you click that, you can write a question to everyone. If you write it to everyone, Björn will see this, and he will facilitate the Q&A session later on. I unfortunately have to leave a little early. So what's the technical community? We are kind of a network of members interested in sharing the knowledge and skills among geoscientists, specifically for petroleum systems, so modeling, geochemistry related things, but also for geosystems focusing on decarbonizations. That's why we call this the Subsurface Systems Modeling webinar and not specifically basin modeling, because we want to include more than just basin modeling or petroleum. Yeah, so if you want to join the community, there's a QR code on the lower right. It should lead you to the page where you can basically become a member. Our technical community at the moment, we have people basically across the globe and different continents. I think our latest additions is Mubarak Al-Hajiri and Carolina Olivares, for example. She will give a presentation earlier next year. Yeah, we have people from service providing companies, operators, quite a mix with different experiences in geochemistry, modeling, or also lower carbon technologies. Just a quick outlook for the upcoming talks, what you can expect. We have already 2 talks scheduled for early next year. Alexander Hartwig from Geosphere will talk about hydrogen, January 28th. You can mark that in your calendar. And then we have a second date already on the notes about pressure modeling, March 25th, 2026. And then we have some lined up talks, no dates currently set in stone, but yeah, those ones are listed. And if you are interested to give a presentation or to contribute, then feel free to reach out to me or any of my colleagues. The EAGE, of course, has the annual convention. It's getting close to the end of the year already, and if you want to submit an abstract for next year's annual convention, then you probably should write up your abstract now, because deadline for submission is January 15th. Most companies have a lengthy process to go through IP and other reviews. So yeah, January 15th is the deadline. So hopefully you will be able to contribute some of your knowledge. At the annual convention, we have 3 dedicated sessions related to petroleum system in some sort. So one about hydrocarbon migration, another one about geothermal, the last one, and then a more traditional one about geochemistry, and petroleum systems. So now back to our main speaker. Balazs Badics has received his master's and PhD at the University of Rouen in Hungary. His master's and PhD focused on source rock and petroleum systems in the Pan-Union Basin. He started his professional career at North Kyoto in the Research Center for Exploration, but then changed more to apply, let's say, exploration activities during while employed for various different companies in Norway. These different companies are a consequence of mostly a consequence of mergers. He has published a significant amount of really good papers about basin modeling, petroleum systems, geochemistry, and play favor analysis. And yeah, with that, I'm delighted to hand over to you. And as a reminder again, please write your questions in the chat box, and Björn will manage those later on. Thank you very much.
Hi, thank you, and then good morning and good afternoon for everyone. First question is, do you see the shared screen now? You see it?
Yes.
Is the sound good?
Yes, we can see it.
Okay,
Yes.
Thank you very much. So basically, thank you very much, and then it's an honor for me to be able to present for such a good audience. You know, I've been doing this for like 25 years now, and some of you, I've read your articles and books back when I was in the university, probably when that picture was taken. So it's an honor to be present. And then basically what I want to do is just to go through some quick things, because this is 45 minutes presentation. And if you know me, I could talk 45 hours about these things, but of course we don't have that time. And then what I want to focus is really the exploration content, not so much on the mathematical part or the scientific part, because we can dare a lot on it, but it's more like how we can apply these things very fast in exploration. And sometimes we don't need very detailed modeling. We just have to look at things in cross-sectional map view and then understand, especially migration. So that's the main message. And it's recorded. I've included a lot of references from a lot of my articles. So articles I wrote with people who are actually in the call, and the references are always indicated, and also there will be very detailed reference list in the recording. So let's start. Basically, the outline is that first I just say what are the objectives in basin modeling and hydrocarbon migration modeling and exploration. What do you want to achieve? And then some of the things in this 45-minute presentation are included very detailed quantitative source rock assessment. That's number one. You always have to know that and explain some techniques which can be used. Also, we look at logs and seismic a little bit very short. And then I will go a lot of case studies, especially in North Sea, which is a typical reef basin, looking at thermal maturity, calibration of thermal maturity, what's the difference if you calibrate with different methods, and then what is the sensitivity of that. I will show shallow marginal basin like the Egerton Basin or Stour Basin as a case study, and I will look into a lot of the hydrocarbon migration examples, what kind of structures and prospects work, what don't work. And then I will show very little about Barents Sea, uplift and erosion, how to estimate, what to calculate, and how to apply it in play mapping. And then towards the end, I will go into very different area, foreland basin, typical Zagros foreland in Iraq and Iran, talking a lot about generation accumulation efficiency and how to model that on a field scale or prospect scale and also basin scale, also looking into shale or shale gas potential calculations. And the very last is about the Petroleum Basin, also very detailed on yet to find and hydrocarbon migration modeling. So on the right hand side, you see a perspective view of the Kurdistan 3D model represented with Adnan. He's in the call. My colleague from Statoil, we did a lot of good work on Iraq and Iran, and that just how powerful these tools could be. So basically, our main goal, what do we want to do? Why are we employed as long as we are employed? We don't know how long we're employed, but hopefully 20 some more years. So we have to understand in any exploration in oil and gas, any kind of prospect, whether it's a stratigraphic trap or structural trap, is there hydrocarbons in it or not? What's the chance of discovery? We call it probability of discovery. Different companies call it PG or PGO or GPOS or post-GO and so on. So what's the chance between 0 and 1? And what's the volume range? Is it in place and recoverable? What's the range? And also, of course, if you work in exploration, you have to estimate other parameters like porosity. First of all, gross thickness, net to gross, porosity, permeability, GOR, BO, BG, expansion factor, recovery factor. But we, as in working with Basin modeling, we have a lot of input into that. For example, on the porosity due to barrier depth and uplift, to the GOR range and the gas expansion factor, or actually the fluid phase, because that is one way to do it with prediction from Basin models. So we have to input a lot of inputs into these calculations and assessments on the fluid properties. I mean, is it the first question? Is it a dry prospect because there is no source rock at all, or the source rock is immature, but there is no contact between the source rock and the prospect? That's the number one thing. And of course, we know that in exploration, about 50–70% of the wells are dry. Only 30–50% are discoveries. So that's the number one thing to tell the exploration team that no, this is not a good prospect because it's no source rock here. Or what is the fluid properties? Is it undersaturated oil? Is it biodegraded oil? Is it oil with a gas cap? Is it a rich gas condensate? Has it been flushed? Is it a dry gas? Or does it have any kind of inert gases which might destroy the quality, which is, for example, CO2, nitrogen, H2S, or even mercury? And all of that basically is the main thing to answer in any kind of prospect review or peer review or project review, and in any kind of farming evaluation or a prospect scale mapping or a large basin scale or a licensing round scale study. This is just an example. It's just, again, the 3D view of Kurdistan with some anticline, and then basically just to illustrate. But I guess all of you who work in exploration, you understand all of these main issues. So what is the most important factors to recognize or assess? What controls the migration and fluid type in an undrilled prospect? I mean, the number one, of course, as we all know, is the source of presence and properties in the drainage area of that single prospect, or the drainage area and the field spill mechanism towards that prospect. We have to know, we have to understand, we have to map the thickness of the source rock as good as possible, the organic richness, COC, corrosion type, hydrogen index, also the kinetics. Different petroleum generation kinetics should be tested. Different thermal maturity models should be tested. Maturity evolution, the timing of maturity versus, for example, uplift, timing of maturity versus trap formation timing, tilting events, water depth evolution events, and so on. So that is the number one. But of course, if you don't have a good source rock in an area, then all the rest is not that relevant anymore. Then you also have to understand secondary migration, and that is the tricky thing. Many times you can model it with different tools, methods. I will go into that a little bit, but sometimes you just have to understand how the system works, looking at simple cross sections and maps. You have to have good carrier beds between the source rock and your actual trap, and also you have to understand field spill migration. You have to understand if there is a gas flushing of a later gas into an earlier oil charge, and you have to understand biodegradation if it's a low temperature trap, and so on. So this is kind of a diagram of a flow chart of what can be done and what kind of models can be used or should be used. But as I show you this example, many times only very quick, simple looks of just 2D sections or maps are enough. You don't have to do a very detailed Basin model of 50 layers, but sometimes, of course, they will give you a lot of more results. So when we go to the first one, quantitative source rock assessment using well data and especially rock eval data, I mean, a lot of work has been done, and I don't want to show all this very nice detailed work published by different people like Jackson et al., Langford, Peterson, Moldovan, Conford, Tyson, Dembinski, Hackley. You can find all the references in the reference list. But what is very important that in any kind of exploration setting, whether it's a frontier area or farming, you have to understand what is your source rock, what is the age, what is the thickness, is it present, is it thinner on the basement ice, is it much thicker, is it much better quality in the basins, under the grabens, what is the organic richness, what is the corrosion type, what is the kinetics you have to use, and of course, there is natural variation in all of this. You have to understand running scenarios. And then one thing I've seen many, many times, especially in frontier settings and companies coming up in new unproven petroleum systems, is the remaining TOC. So when we take a very good example from the very good work published by Don Jarvie et al. Already like 2007 from different American shale oil plays, they explained very nicely what is the residual hydrocarbon, what is the residual carbon, and what is the labile carbon, which has been converted into oil and gas. And what I've seen many places is that companies and countries come up with source rocks which are not that good. You know, they don't have like 1%, at least 1% TOC. To So what you have to understand, in every single basin, if there is a good source rock, even if it's very deeply buried, even if it's very mature, it always has minimum 1–2% residual TOC. And if it doesn't, it never had. So that's number one. You have to really understand and map your source rock. And I just show one example. You can show examples from any place, from Angola, Namibia, Pannonian Basin, and so on. This one is from Norwegian Sea. On the left-hand side, you see a very shallow, very good quality source rock in a Helgeland Basin in mid-Norway. There you see on the left-hand side the TOC, histogram in depth, and then the hydrogen index. And you see this has about 6–7% TOC, very good quality. Hydrogen index 300, 350, 400. This is the typical Upper Jurassic source rock of mid-Norway called the speck formation. It's immature, vitrinite 0.4. It's about 6% on average, and 300 hydrogen index, very, very good quality. The same source rock is drilled about 250 wells in mid-Norway, and then the TOC goes down to like 2–3% in a deep basin, for example, in this well, which has vitrinite 1.7, dry gas window. But you see the TOC is not zero. Hydrogen index goes down to 15 or 20 or 25 and so on. But what is important that the TOC is never zero. So if you are shown in any basin, any area, any farming brochure that the TOC is very, very low, then probably was never high. Basically, that's it. And then you have to really do it. And if you have lots of wells, of course, you have to create TOC maps, hydrogen index maps. You have to reconstruct the original TOC using the different methods I showed in the first slide. But this is actually quite common, that companies chasing new plays or coming up with hypothetical new plays, they don't have a really good source rock. And that's very, very big danger already from day one, because you have to have a good source rock in order to have a good play. When we move to a more detailed estimation, because it's lack of time, we published a very detailed case study of how to do it in interpretation in 2015 from the South Viking Graben in Norway, from the Frigg and Frøy area. You see the map on the left-hand side showing Norway and where the red box is. And on the right-hand side, you see the zoomed-in map with the structure elements. And here we did very detailed study using about 30 wells and the seismic, 3D seismic, good quality. So this is an area we know that there is source, but of course the variation in the thickness is significant. Also maturity variation is significant. This is the northern part of the Utsira High. The maturity is lost towards the east. So basically any structure drilled east of the Utsira High are dry because there is no migration, because there is no maturity. And since that work, about 5 new wells were drilled and they all dry. So people really chase these things, but it's just a fundamental issue, for example, maturity. But you see that even that area using 30 wells and seismic, there are big variations between the drop in the thicknesses, going from 0, being eroded, to like 200–400 meters in the basin center. Same with the underlying header source rock. And in this case study, we used a lot of logs, tried to create a new way of estimating logs, estimating TOC from logs, trying to modify or rebuild the PSA method, very many of you know. And when you look in real data, this is about 30 wells and I don't know how many log measurements. So basically hundreds, thousands. And then you see that there is no clear relationship between sonic velocity, gamma ray, VP, resistivity, and density, and the actual measured TOC. But of course, when you use more logs together and also try to look at the acoustic impedance, you can come up with nice calibration of the logs to the TOC content and also to the logs to the seismic. And then using the nicely published methods by Helge Røseth and others, Marita Garding and others from Statoil back in 2011, who published that the very good quality source rocks show always a class 4 AVO, and the soft response at the top and the hard response at the base. You can quantitatively map these things in any kind of setting. Of course, if you want to have good quality maps, you have to have good quality 3D seismic. And we had in this case, in this presentation, I did not show the good quality 3D seismic because then you have to get access or approval from CGG, PGS, and so on, and it's really, really difficult. So here, this is the published one from the interpretation article. And then also what I can mention that the method works really well for good source rocks. It doesn't work very well for not so good source rocks, but I recommend you to look at, for example, the absolute maximum negative amplitude or average negative amplitude RMS map of the top source rock, because usually your top source rock will be a soft negative response because it has much lower density and much higher anisotropy. And then also you can look at the positive amplitudes, maximum positive amplitude, the RMS amplitude at the base of the source rock. And you can map really nicely, beautifully, if you have good quality 3D seismic, whether it's North Sea or Angola or Brazil and so on, post-salt, probably you would see very nicely the edges where it's not deposited. You see the soft sediment, like slump scars and all that. So that's a really good method to quantify it on seismic. And more details are in the article if you want to see. So just one thing, when you are working with very, very large models, a nice tool to calibrate your heat flow has been developed by Petroleum people and people from, I think, Aarhus University back about 2008, 2010, which is called heat flow calibration. And you find a lot more in the very famous Basin modeling book by Thomas Hanschel and Armin. But actually, I recommend you that this is really, really time-saving effort, because when we are talking about very, very large models, which I will show later, for example, on the right-hand side, you see the upper one from Iraq, we built with Adnan. It has about 160 wells with temperature and about, I don't know, half million square kilometers. And then the one from Hungary I built, that has about 600 wells or 700 wells with temperature. So to calibrate that manually, that is really, really challenging and time consuming. So when you look at similar size models from the North Sea, I have, for example, North Viking Graben, has about 600 wells. I mean, that is very difficult. So this tool helps you to calibrate, and I do not know if this tool is available, for example, in IFP Temispec or in Trinity, but definitely in Petromod it's available. And what you do is that you run it, and you recognize that some actual temperature measurements were not that correct, because if you have one well which is very different from the other 5 next to it, then probably the one well is not that correct. So basically you run it not just once, you run it again and again, and you calibrate and you calibrate, and then basically this tool runs about 8 times. Then it creates you the new heat flow maps. Then you check again the key wells, the best quality maps and wells, and then you run again. So basically you save a lot of time. Manually doing it for more than 100 wells is extremely time consuming. So this is just on the calibration. When we move to the North Sea and looking at the migration issues and what companies thought and what is the result, is that basically I published once in 23 at the EAGE in Vienna and also in 24 EAGE in Oslo, the statistics of what the companies thought the main pre-drill risk was in North Sea. And the first talk was, which you have the extended abstract and also the references, that looked back from the beginning of exploration in Norway in 1966. And then it looked at every 10 years, how many discoveries were made and how many wells were drilled and how many were dry. So basically, and here is the same kind of categorization what NPD in Norway is using to find out what is the main reason for failure. Was it the charge, which is presence of source rock, maturity of source rock and migration, or presence and quality of trap and top seal, or presence and quality of reservoir? And basically, if you look at all these wells, I don't know how many altogether, like 1,000 or so, basically, before drilling, most companies assumed that either reservoir or trap are the main risk. But actually, after drilling, they find out that the charge, especially the hydrocarbon migration, was the reason for failure. And you see per decade how these things evolved. And actually, even everybody says that North Sea is very well proven and source rocks everywhere and maturity. More than half of the wells fail, especially in the last 20 years on migration, which is quite strange. Like, why is that? And then you have a 4-page abstract in the EAGE for all the details on the statistics and the examples. And then in the EAGE 24, I focus the last 5 years, and then it's every year how many wells are drilled, how many discoveries, how many dry wells. And then the statistics is very similar, that after drilling, companies blame about half of the dry wells on migration failures. And then again, in this one, in the 4-page abstract, you find a lot of examples and statistics, but now I will show a couple of them here in this presentation. First of all, calibration of vitrinite reflectance models. We know that everybody has been using the Sweeney and Burnham excellent kinetics from 1990. I don't know how many times it has been referenced, like 10,000 times. It's really a beautiful work. But we know that vitrinite reflectance models have been evolving with time, and other people propose other type of kinetics, like Nielsen et al. And Ritter and so on. And also Alan Burnham himself came up with newer works. in 2016 and 19 and published it. And there are big differences, especially when you look at shallow burial. We know that the older EZR curve is a little bit over predicting maturity in shallow sections, but under predicting maturity in deeper sections. When you look at the shallow well in the Egerton Basin, the difference can be like 0.2, 0.3 vitrinite. That is quite significant. When you look at deep basins, it's similar. This one is from shallow. This one is very deep from the central Viking Graben. But it's very important that when you calibrate to your vitrinite reflectance, you run different kinetic schemes because the results can be different. This one is from the EAGE Talk 23 in Vienna, is that now the map is calibrated, or the CD Basin model is calibrated to the vitrinite, new vitrinite kinetics from Alan Burnham, which is giving you a little bit fewer areas of the early oil, peak oil, and late oil maturity. If you calibrate, because this is a very shallow basin located just southwest of Stavanger, and many dry wells are found here. So basically, if you run it back in like 2005 to 10, when this new kinetics was not available, then you have over prediction of the maturity. And we also know that vitrinite is not equivalent for oil and gas generative kinetics. It's just a proxy. But people use this in numerous companies to show that it is still valid and it's generating basin. But when you calibrate to the newest kinetics from Burnham 2019, the actual main oil and peak oil zones are shrinking. And the dark green areas where it's just very early oil are not that many. And then the thing is that in this area, Equinor, back in the early 90s, they drilled the first two discoveries, the EMA main and the EMA southwest segments. And already at that time, in 1990 and 1993, they published two very good articles in Organic Geochemistry and in one of the Geosoc books, that it's very high risk of low maturity in this basin. And since that time, many other companies went in and drilled very many dry wells, like Paladin, then Norsk Hydro, Talisman, Premier, Lundin, Wintershall, and Repsol, all over these years. And then here they tried to calibrate using probably the older vitrinite kinetics, and assumed also that when it is just early oil maturity, it's generating a lot of volume, but it's not. You have to really be careful showing these maps to management or colleagues, because the early oil, you know that oil and gas generation is exponential. So when you are in the very early phase, between vitrinite 0.55 and 0.7, you generate very small amounts. And those small amounts are enough to just give you some shows. But basically all of these companies went into this area. It's using beautiful, good quality 3D seismic. Very many salt domes exist. Very many structures are still undrilled. The problem is that it's just too shallow. And then it's very important to use the best and newest vitrinite kinetics to calibrate all your wells too. So that is again explained more in the EAGE Vienna extended abstract. If you move to the northern part of North Sea, again, very many people, very good articles have been written already in the late 90s and early 2000s about different oil families and field spill migration. But again, here some companies assumed all the time that it's source rocks everywhere, apodrosic source rocks, it's mature everywhere, so you drill anywhere and charge is not an issue. But it's actually not true. When you look at already these first articles from like Horsted and Larter 97, they identified that the graben between Åsberg and Brage is immature. Also, the large area of Stor Basin between Brage field and Troll is immature. And then basically, when you drill prospects between Åsberg and Brage, they will not be charged because it's no direct migration from that small graben, but it's much more a very nice field spill migration from the north, from Vestlefrik to Åsberg east to the so-called Whiskeyland and to Brage Stadfjord. The same from Åsberg south to Brage, Upper Jurassic, and then to Troll. So that was published. Later on, other people picked up and did much more work on it. On the other hand, in the Tompen area, Jorgen Johannessen from Statoil and colleagues published very nice work showing how the UK side, Brent, and the Stadfjord field, and also the Murchison Delta and Stadfjord North are filled via field spill, but also explaining that some of the grabens just next to Stadfjord, for example, are not mature. And since then, again, many companies drilled wells, also between Snorre and Tordis Vigdis, in these red areas, and I will show more detailed maps later. So basically, it is not the same that if you have a giant field like Statfjord, that you drill in the hanging wall of Statfjord and you find oil. Because if Statfjord field was not filled from that direction, but it was coming from the southwest, you can have many dry wells next to these giant fields. And then if you go back to the Åsberg and Brage area, this is new publication from Stephen Hay again, 2002 from Statoil, explaining how the detailed migration is going on from the northern kitchen to Vestlafrik to different Jurassic Age reservoirs like Brent, Statfjord, and Cook, to Åsberg East, and then Åsberg Zeta, then the Viskeland, and then Brage. Basically, just now, I think a couple of weeks ago, OKEA announced a quite nice discovery in the northwestern area in Brage called Talisker. That's lying in the same migration path. Also, my colleague Torsten Garlick, he published a very nice article using aromatic parameters on these migration distances using the same area. But just remember that it is very, very important that if you have a prospect between Åsberg and Brage, like Equinor did a couple of years ago, one called, I don't know the name, Hellenesset or something like that here, that is not charged from the Graben because the Graben is immature here. So still now, very many companies go for these prospects because they assume that it's migration very easy and so on, but it's just not. But when you are on the migration pathway, then you make nice discoveries, like Talisker West. When you are in the immature hanging wall Graben, like they drilled this Hellenesset, then it's dry because it's not coming from this small kitchen, but it's a field spill from north, and also Åsberg has a huge kitchen in the northwest. So some of it has been shown by me in 23 at the EAGE Vienna, when I went through all the North Sea in Norway, starting from Central Graben, South Viking Graben, and North Viking Graben, and I highlighted these areas. And then this is just a summary on the left-hand side, that even if North Sea has very, very good quality Upper Jurassic source rock and very good maturity in most places, you have to really look at the maps, because just next to these giant fields like Statfjord and Snorre and Åsberg, there are many, many hanging wall grabens where the source rocks are not deep enough, they are not mature. So the Dropne and Heather are not generating in that small hanging wall graben, and that's why a lot of dry wells have been drilled. Like I mentioned, this Hellenesset, I think 2020, between Åsberg and Brage. Then these string of wells northwest of Snorre field, 33C6, 3362, 910, 911, or the ones drilled in the small graben between Snorre field and Basin field. They are the 34, 715, 735, 736, and they are drilled in the last 10 years, some of them. So just remember, this kind of setting can be also in other rift basins, like in the Sirte Basin in Libya, or in the Bombay Basin, or and so on. So that is, you have to look at the actual kitchens, and you can't assume that it will be generating in everywhere. And I think it might be very easy and straightforward to all of you here, but many, many times I've seen exploration companies just assuming maturity and migration from all over the place in rift basin, but it's just not. So we just look at some cross sections as a kind of exercise very quickly. And these are real cross sections. This one is from the Lindgraben, going from southwest to northeast, and then it's just from another publication from Chris Jackson showing the salt tectonics here. But this is real section, real geometry. And then you assume that the dark gray is the Upper Jurassic source rock, Dropne and Heather. Then this lighter gray is the Middle Jurassic reservoirs. Here it's called Tannes and Bryne, or Hugin and Sleipner. It's time equivalent of the Brent. But you see that if we have 5 unnamed prospects, just call them A, B, C, and D, they are roughly real. Some of them are still undrilled. That how many of them can be charged? And remember that now most of these have beautiful 3D seismic. They are giant undrilled closures of like 250 million barrel potential. But when you look at the maturity, and oil generation in this area is about starting at 3,500 meters, you have to map the drainage area of each prospect. And of course, this is just a 2D section. It is not ideal. You have to look at the map. But many companies just assume that, yes, it's a very large closure. It's beautiful, maybe amplitude anomaly on the crest and so on. But you know, it's many of them. It's just not going to be discoveries because the source rock in their respective drainage area is not mature. And also, you cannot assume field spill when you have a structure, for example, like B, in order from B to field speed to C, D, and E, you have to have an awful big column building up, which is not very likely. So basically, this is just an example showing, it's one of my internal courses here I'm doing in the company, that people have to rank which one will be charged, which one will not be charged. And if you look at this example, the only ones which are really very high likely to be charged are the A and B, because that's where their drainage area, the source rock, is mature, and the rest is not. And actually, this is some of them have been drilled already and dry, and some are undrilled and still there. So this is just one very simple exercise when you look at cross sections of the margins of these rift gravens. When you look at basin boundary faults, they are also playing a very, very important role. Many times you have very large faults, and this is again a real example. This is the western part of the eastern part of Thumb and Spur. So basically the western big boundary fault is here. And then you have the good Triassic, then Lower Jurassic Statfjord, then Cook and Drake, and then Upper Jurassic Heather and Dropne sections. But that is immature on the crest of the Halt and Spur. And then we know that when you drill a little bit further away, but it's only like 10 kilometers from the main kitchen, but that is separated by different faults, you drill a dry well. And then basically, when we, I just see some questions coming. But then later on, in 2012, discovery well was made. This is actually the Garantiana discovery into the segment, which is just directly next to the regenerative kitchen. There, the Dropne source rock and the Heather source rocks are directly juxtaposed to the Cook reservoir in that fault segment. And the appraisal well was drilled in 2014, and that also found oil and the oil leg. But later on, companies want to develop that, and this is brand new stuff. Is the Garantiana field development going on? They drilled the dry well in 2005, in May, June, and then in August, in fault segments which are beyond the first fault segment. So in such cases, very important to map in 2D, to look at cross sections, really a series of cross sections or thickness maps between the top reservoir and your source rock, that which one can be charged and which one not. But remember, this is real case example from real seismic. I can't show you the real seismic behind, but basically that shows you that when you are in a rift basin, sometimes your faults will delimit your migration and only your closest fault blocks will be charged and the rest will not be charged. So it's very important to remember. And I guess similar settings are in the other rift basins in the world, like Bohai Bay, Kam Bay, the Emperdones Basin, Ukraine, Gulf of Suez, very heavily explored, Halten Terrace, Hammerfest Basin in Barents Sea, the Malay Basin, Thai Basin, Sudan Basin, Sirte Basin in Libya, Songlia in China. So this is very important, and it can lead to lots of negative surprises. When we look at the last example from this area, then this is where we have lots of different reservoirs, and then in this case is the thick Brent group, where you have the Tarbert, very good quality, and then the Uzbek and Native Ranok underneath, very good quality reservoirs, and you can have Lower Jurassic Cook. And this is just the other side of the graben. This is, for example, the Uzbek area, but you can apply it to the Gullfaks area or the Visund area. And here, it's again what is important, that the reservoirs which are directly connected to the actively generating kitchen, actively generating source, they are very easily charged, but it's not true for the reservoirs which are separated and vertically below 200-300 meters, because then oil and gas will not migrate downwards, it will only migrate to the easiest things. And in case that reservoir is filled to spill and the fault is leaking, then you have cross-fault migration. This is just an example, but you see that many cases, and especially in the Uzbek area and also Gullfaks area, these reservoirs are there in every well. Even the Statfjord you can add underneath. And the companies in the 80s, 90s drilled always Tarbert, Uzbek, Cook, Statfjord. And they found oil and gas in Tarbert, but not in Uzbek and Cook sometimes, because of the geometry. So that you can show in numerous cross sections. Just have to look at 2D cross sections from Uzbek South, from Uzbek Main, from Gullfaks, from Kvitebjörn, from Visund, from Snorre, that only the ones which are directly juxtaposed to the kitchen, to the source of them, those are really working. So that is just part of the quick look techniques. So you can summarize that rift basins, when you have big master faults delimiting the grabens, you have very good and easy migration to the reservoirs which are directly juxtaposed and directly connected to these actively expanding source rocks. But when you have some basement high or some focus points, then the shallower Paleocene, Eocene sands or upper Cretaceous chalk can be charged easily. But in cases where your reservoir is, for example, Triassic or Rotliegend Permian sands, which are below that kind of good source rock, like the Central Graben in many places in UK or in Norway sector, these are not charged. They are just dry. Or you can have Upper Jurassic or Middle Jurassic sands in migration shadow because they are beyond basement highs, like the Utsira High. Or you can have tilting reservoirs, for example, in the southern part of Viking Graben. These Paleocene Eocene sands tilt up towards the UK sector to the west. And then many wells, about 10-15 wells drilled in Norway, but the migration goes up from Jurassic highs and then goes back towards the UK sector, not the Norwegian sector. So this is just a summary of the rift basins. And then I'll just show you some of the key articles here. So these are the bold ones I have been writing myself or contributing to. And then the rest is just very, very useful. And these are the other examples I showed. So I keep some time to it. And then this is the second part of the North Sea articles. And this is the very famous one from Satoir, Hegeruset, and the others on the source rock seismic method first published. I really recommend that. So when we move to Barents Sea, and then just quickly on estimating erosion and uplift. Of course, we know that in basins, it's very, very important to estimate erosion and calculate it, calculate different magnitudes in absolute meter, like net erosion, and also the timing, because the erosion has very high effects. It can have much higher maturity than expected for that depth. You can have much earlier timing of hydrocarbon generation and migration. You can have spill and destruction of hydrocarbons and remigration due to tilting. And then usually the earlier the erosion is, it's usually worse than the later one. So also, of course, a very high effect on the porosity reduction of the reservoirs. You can have pressure drop, gas caps, topsy breach, and so on. So this was published by us in 2019 EAGE London. This is a combined view of 21 detailed 3D basin models of the Barents Sea, showing the top Jurassic, the top Hackingham, and then how we estimated the erosion. And then we use that also in play mapping. When we create any kind of nice 3D model, you have very good thickness maps already. For example, source of thickness, also reservoir thickness and seal thickness. You can, of course, your goal is to create source of maturity maps. And then you can combine them also, of course, source of TOC map or quantity or quality map. You can combine them with erosion maps, erosion timing, when the erosion actually took place, and then also when the hydrocarbon generation took place. And then you can have reservoir porosity maps coming out from the 3D basin model, and the seal thickness and seal strength maps. And basically, when you combine them, this is on the right-hand side, shows you the present day calculated maturity of the top Jurassic of the Hackingham Formation, keeping in mind that early oil generation is very, very little generating, and then peak oil is this other color. And then when you reach the western part, it's very, very deeply buried, and basically it's just gas and dry gas, but also bad timing because it took place very, very early. So basically all of that you can combine into play maps. When you combine the source, the reservoir, and the seal maps into combined play segment maps. And then this is also very, very useful and very, very good to use 3D basin modeling for that. So that one we published in EAGE London in the 4-page abstract is available. And then I show you the references here. And then this one was the one I talked about. And some other are quite new and very, very good quality references on the erosion of the Barents Sea. I think we have one more. No. So when we move to the Zagros foreland, it's different kind of basin. And then here I show you 3 different articles we have done. One with Adnan Akrawi and GeoArabia, that's the detailed one, and 2 very detailed presentations at the Geo16 conference. So here the basin model included whole country of Iraq and Kuwait and the most of western Iran. 23 detailed depth maps were created from top basement to surface. Very detailed erosion model in the Zagros fault bed in the east. And then just about the size, it's 2 by 2 kilometers, about 30 wells, 10 outcrops, 160 wells, 30 wells with source of data, 160 wells with temperature data. And we wanted to map in quantitatively the middle and upper Jurassic source rocks, and then look at the maturity and generated volumes and also per range area. So it's just some images from the article that how useful this can be for regional evaluation. We use this kind of model from basically 2005 or so. We started to build it, and then it was used in a lot of licensing rounds within Iraq, and also different project and prospect assessments in Iraq and Iran during the time. And then Statoil allowed us to publish it in 2014. So that shows you the different tectonic regimes. And then some 2D geometries. We have, of course, these 23 maps. These are an example of top Middle Jurassic source rock depth map on the right-hand side, and some cross sections. Of course, when we reach this very, very extreme folded belt in Kurdistan, is very complicated. So, of course, here you need a lot more work. And this was just a very simple exercise regarding that, because only here you could spend years to create a much better model. But then the objective was to test different kinetics, and these are sulfur-rich source rocks, type 2S, most of it. And then basically we tested different kinetics and looked at mass balance for proven fields and also for undrilled prospects. On the right-hand side, you see the detailed stratigraphy. And then this is just an example, again, that 3D Basin model is very, very useful. You take the thickness map of, for example, this Middle Jurassic source rock, some colleagues here, and then the TOC maps, other index map, and the source potential index from the Demoism. And then you calculate the maturity, and then you can also calculate how much has been generated in a 2-kilometer cell model. And then you see that the largest volumes are generated in southeastern Iraq and southwestern Iran, close to Rumaila, West Kurna, and Ahwaz fields. And then we looked at also the timing of generation. We're looking at different kinetic scenarios, and you see all the 5 different type 2S kinetics. And then we looked at the drainage area mass balance. In this article, we published the Kirkuk, East Baghdad, and Majnun fields. It's very easy to map the drainage area. It's in, for example, in Kirkuk, 2,600 square kilometers, and about 200 billion barrel oil has been generated from the 3 source rocks that we mapped. And then we know roughly how much is in place. And then you can calculate the so-called generation accumulation efficiency. This is per field or per drainage area. So this one is detailed in the article, but we've done the same also for the 3 source rocks, the Lower Cretaceous, the Upper Jurassic Naukarekon, and the Middle Jurassic Sargalu. And then we've done the same for these different tectonic zones or basin, sub-basins or provinces. So that you can compare with other people, USGS people, Abrant and Verma, and also Pittman. They published on how much is the yet to find potential. And then in this article, which is the GeoReview article, we compared it with the generated volume from the different source rocks in different tectonic zones, and then how much is the discovered volume in place so far. So what is the efficiency? And you can see that in some kind of foreland basins, it's about 3 to 6%. And it's very similar to what Jean-Jacques Bittot published globally in his very good first break article around 2012 or 10, I think. So again, just quickly, we repeated this work in Kurdistan for the 2016 Geo conference, where what I did is I took lots of published maps of the different anticlines, which were very high focus at that time in northeastern Iraq. And you see it's about 20 of them. And the companies published them on the internet, on their company webpage, or in the so-called reserve evaluation report or competent person report, which is basically focusing on the reserves. And then based on that, I could build the whole detailed Petroleum model of the whole Kurdistan. And then that was basically refined our Iraq model with a 1 by 1 kilometer. And then, of course, here we know that the northeastern part is extremely thrusted and folded. And we didn't spend years on that because we know that it's very, very destructive for oil and gas preservation. But basically, we could calculate the same, how much oil is generated and how much is destroyed in the high folded zone, low folded zone, and foothills. And then in this purple again is the Kirkuk field in the middle. So that can be used in for example, evaluating oil versus gas or dry gas versus biodegraded oil and so on. So there is a lot of anticlines undrilled still. Probably I have not been following up what's been going on in Kurdistan, but I would say that about half of the anticlines are still prospective, and this is exactly how you can try to estimate what's the phase. So the last thing we did is to try to make analogs with the US shale oil and gas space. Remember, this was 10 years ago, and then international was not as, probably has not picked up as much as we thought 10 years ago, international shale oil and shale gas. But if you look at the upper and middle Jurassic of Iraq and Iran, and look at the source of quality, it's very similar to many of the proven US plays, but of course politics and economy and facilities and costs and so on, it's not taken into account here. But this is again available as an extended abstract. So as time is running out, I just show you the references, and then from the last one I just show quickly. So these were the references we have, and these are the two geo presentations, and one is the detailed Geo-Arabia article. So we go to the last area, the Hungarian case study. I tell you that this is published in this new Geologic Society special publication. It's a very detailed article, about 100 pages, where you can see all the details, and then it's an extremely detailed model. It's a 1 by 1 kilometer cells, 24 detailed depth maps, about 450 wells with source rock data, 170 with lignite data, and about 700 with temperature data that has been used. And then basically it's similar method to estimate volume, maturity, and generation, and basically migration of hydrocarbons. And again, in the different years before, we published with, for example, Viktor Lemberkovich, who is also in this call, a nice 3D model from the Kiskunhalas part. It's a much smaller model, but it's much higher resolution, but 100 by 100 meter grids. And also before about the Mako trough, that's in 2011, that is focusing on the shale gas and shale oil potential. So that has been reused and rebuilt, and basically the 2014 covering the whole country. And then a lot of details can be found in this article. I just show you very quickly because time is running out. That, for example, if you take an area in the southwestern part of Hungary, this is Croatia here, this is the southwestern part, so-called Drava and Somogy basins. First, you start with very detailed polygeographic maps, and then you see here the gray is where you have very good quality middle Miocene source rocks, and then the blue is where you have kind of reefs and carbonates, and the pink is, for example, evaporites. So it's a lot of wells went into it. Only here is about 200-300 wells drilled. And then you do the same, you estimate maturity by calibrating lignite and temperature. On the upper left, you see the depth map of the base tertiary, which is here in about lower Miocene. And then on the lower part, you see the maturity at the lower Miocene. And then on the lower middle, you see the maturity at the top of the middle Miocene. And then you see the migration vectors calculated, and you see the proven fields. And I just mentioned that this field, this so-called Pettem or Lakocha, was discovered by, I think, Hungarian Horizon around 2019 or 20. And this is onshore, and it's about 20 to 30 million barrel recoverable. So this was found very late in the exploration, and there's still potential here. And then basically this kind of 3D basin modeling is very, very useful to find out the maturity zones and even the migration. But of course, this cannot be used for prospect scale exploration. I just show quickly this last one from the middle Miocene, inverted strike slip graben. We published with Viktor Lemberkovich and others. And then here, the basin model was much smaller, but higher resolution. And then basically you see the input, very many different horizons in the middle and upper Miocene. And then basically the similar method was used, looking at maturity, calibrating it to lignite and temperature, looking at different source rock levels, looking at migration pathways, and then trying to estimate in which parts of that graben you have still undrilled closures, which chance of hydrocarbons. And then basically the very last one I have is the work we did on this Hungarian potential shale gas play, or basin-centered gas at that time it was called. It was like a hype 2008-10. A small company called Falcon TXM, they claimed that the middle part of this Mako trough is full of gas. And then I was quite skeptical, and we put together 3 different papers. One is in Petroleum Geoscience, trying to calculate the generated volume of gas and oil. And basically, we had the view that it's just not filled with gas. By calculating the amount of gas and oil generated using basin modeling technique, and then the amount of pore space. So this is a section they had initially, like 2007, that they claim that all these middle and upper Miocene formations are filled with gas. And then the source rocks are not that great quality. You see this deep well with about only 1% TOC. And we calculated the generated volume and compared it to the pore space using the logs. And then basically it turned out that the generated volume of gas is just much, much lower. You cannot fill the whole basin with gas. So this basin center gas is not that real. So basically that's it. And the last slide is just the main takeaways, that our goal in exploration when we do basin and petroleum system modeling is to really predict the charge and migration into an undralled prospect, the probability of discovery, and the volume range, and the fluid properties. And this will depend on the source rock presence and properties in the drainage area of that actual prospect. You have to do very good work finding, really mapping the source rock thickness, using also rockable data wells, well logs, and seismic. Use 3D seismic, absolute minimum amplitude, +4 AVO. Look at the organic richness. Try to back calculate the initial richness, and look at different corrosion kinetics to understand the volume generated and the timing. Thermometricity and drainage area will be most important, and also look at the secondary migration, especially geometries in 2D and 3D, if there is a good carrier or good connection between the source rock to the reservoirs or not. And then basically, I would say that sometimes no advanced 3D modeling is needed, only a very good understanding of the geometry and common sense. So basically that's it. And then just you can read up the questions. I will show you the references at the end because they are also useful if it's recorded. So this is the references of the Pannonian Basin first, and the bold ones are the ones I have used a lot of figures from. And then these are also the others. And then basically at the end, I have included lots of references on general source rocks and migration. I guess most of you know them all. I just put them up for people. And then basically that's it. And I have probably exceeded my time, but in the beginning, the introduction was also longer. And then basically thank you for the nice atmosphere and the work for 24 years so far with all these companies who slowly eat each other. And then basically that's it. And I'm not sure how much time we have for the questions. I probably exceeded about 10 minutes the initial talk.
Yes, Balazs is Bjorn again. Well, thanks for the presentation. Don't worry about the time. I'm sure we'll have enough time for to go through the questions that we have so far. And once again, I always like having lots of references. I think that's a really useful fact. And so there will be a recording, and so you'll be able to look at the reference lists in the recording. They'll be included. So that's really nice. So we'll start with some of the questions, and I'll just go through and read them quickly. They're in the chat box, but we'll just start with a question from Friedemann. How do you tackle the challenge of source rock thickness evaluation, which you identified as a very important factor for the volumetric analysis? Do you always map the source rock and apply either seismic amplitude analysis or petrophysical work?
Yeah, it depends. I mean, if you have very good quality seismic and you have good well ties, basically you just have to map it. But many times people focus only on the reservoir. They have a prospect and they have a reservoir and they don't want to map the top and the source rock. But of course, for example, in North Sea or Norwegian Sea, you always have to map the top because that's usually the BCU, very easy to map. So it's not a big deal. But for example, the base Dropne or the base header, sometimes, I mean, base header is the top brand. So I would say that in North Sea and Norwegian Sea, usually it is okay. But when you are in a frontier setting or in another area, you have to really understand and you have to have an uncertainty on it. And you basically run kind of probabilistic scenario that what if your source rock is only 50 meters? When you really do detailed work in the North Sea, you will see that the Dropne source rock is not that thick actually, not even in the basin centers. When you map the base, it's usually in the range of 100-200 meter maximum. So it's not like the underlying header source rock that can be a kilometer thick. But when you do real detailed well type and you focus on the source rock thickness, I think you understand basically the volumes generated much better than just assuming. For example, it's very likely that in the northern North Sea, most of the volumes are actually coming from the header source rock, not the drop net. Simply the thickness is larger. But of course, when you have petrophysics, you have to use it, and you have to always use scenarios like probabilistic, like ranges and so on.
Okay, very good. Then we have next question from Norman Euros. There have been some recent articles discussing the role of faults in migration, either as conduits or seal. What is your opinion on this? Are faults necessary for a successful prospect, or the need for this, or is the need for this element overestimated? So
yeah, it's complex. You can talk a lot about it. We all know, but basically, what you see is that faults are not sealing or leaking; they are changing their behavior. I mean, we know that when they are very deeply buried above like 120 Celsius, you have quartz cementation. Most of them are sealing, but remember that they are sealing cross fault. But when you have fault along, then I mean, basically, it's much more likely that if you have sealing fault today, but in the other side where the source rock is generating, that is actually helping for the hydrocarbons to move upwards, whereas on the other side of the fault you see different fault segments and different pressure regimes. So I think it's a complex thing. You can't really answer it in one sentence. You have to look at the temperature today and the temperature evolution, also how deep the fault is now, and then remember that what fault is sealing today might not have been sealing 20 million years ago. And then migration could go in, but now it is the limiting factor. And yeah, so basically you have to look at the case by case, looking at cross sections. And for example, I don't want to go very detailed, but you can go up here to see that most of the fields in North Sea are sealed by faults, but the actual fault is the juxtaposition of a shale source to the actual reservoir. So in this case, most of these cases, these are real cases, the fault is sealing or not well. I mean, it is juxtaposing a very low permeability, tight expelling source rock to a very high permeability, high porosity reservoir. So that is, in a way, yes, maybe sealing fault, but still migration going into it because of the different permeabilities. So that, but it can be a very complex answer to this because it can be very complicated setting.
Yeah, but as you said, this is something that's been going on ever since the advent of petroleum systems modeling. So 30, 40 years, it's an important question. Right, next one here from Tiago. Thanks for the great talk. In the automatic calibration to heat flow or thermal gradient, is the model looking into the borehole data or other data, calibrated 1D models or both? And is there any prioritization regarding data quality or the 1D models? And is this just a present day calibration, or does the model recover past heat flow and thermal regimes via the 1D models and or inputs from tectonics? Okay,
actually, I'm reading it here also. So yeah, it's a long question. It's
yeah.
I mean, basically, what do you put in? This is just it's just a tool which is basically an AI thing developed nearly 20 years ago by very good people here, probably Thomas Hanschel and Armin and Jesper, or some Nielsen, I'm not sure. But what it does is that if you have only bad quality borehole BHT data or better quality log derived temperatures or very good quality DST temperatures or steady state, it's up to you. I mean, what you put in, for example, in this Hungarian case, is an enormous amount of temperature data put in, like 5,000. I don't remember the number. So basically, look at 60 wells with steady state temperatures. It's really very difficult to get, and 600 with DST. And then basically, you have a statistical data set, and then it looks at the input heat flow or thermal gradient you put in, and then what has been calculated. But there will be a difference. And then it looks at the root mean square of the difference, and then it adjusts the heat flow or the thermal gradient to match it. But of course, because you have so many wells, so many temperature data, you run it, and then you will still have errors. But then basically it's an error minimizing way. But maybe if Thomas is in the call, he can explain more the mathematical background of it. Maybe it's in the book
Okay.
also, Björn, I don't know.
Yeah. Yeah, this is a topic for a course long. You'd need have at least a day to go through this. An important point. Next one from Attila. Do you have experience working in volcanic basins with complex intrusions, volcanic architecture? What are the main challenges there in terms of source rock maturation modeling, migration trapping, etc.?
Yes, and basically here, and I know Attila very well, it's basically in Norway, you have a very good example of the Vøring Basin, Mør Basin. You have very many sills, so basically magmatic sills, and enormous good work has been done by the Sverre Planke's group, the VBPR, Volcanic Basin Margin Research Group, but also in the present day basin modeling tools like Petromod, probably also TennisPack, you can model thermal intrusions from the beginning. You developed that kind of technique in the 90s, and basically it takes into consideration the volume and the mass of the intruded layer, and then it calculates very nicely that you put in for example, a seal which is 10 meters thick, but it's 1000 Celsius basalt, how fast it cools down and how big volume it changes. And the rule of thumb is that if you put in 100 meter thick or 10 meter thick intruded volume, it will create a thermal aureola, which is the same volume twice. So basically 10 meter will destroy above and below 5 meter. 100 meter will destroy 50 meter above and below. And then the time of the cooling is just explained by the mathematics. But actually, if you look at the exploration scale, most important problem, I would say, with these volcanic seals is that they create a very large peak in the generation when they intrude. And we know that in Vøring Basin, that is Paleocene-Eocene breakup event about 55 million years ago. So basically, they intruded a lot of these Middle Cretaceous long source rocks, and they created a peak generation event. They heated up the water. They create these supercritical hydrothermal vents coming at the edges of these hills. And that is not that good because you had not all the traps which are there now. They were not existing at that time, or they were not the same size and shape. But most of the generation took place at that time very, very fast. And that is now 55 million years ago. And then if you did not have a lot of subsidence afterwards, you lost a lot of hydrocarbons. So, but I guess that if you contact me privately, I can tell you a lot of articles from both Sverre Planck and also Daniel Schmidt from Geomodeling Solutions. They've done a lot of published work and very good even videos on this type of thing.
Well, that's a good topic. Okay, then we have the next one from David.
Yeah.
The demonstration of 40 to 50% dry holes being due to charge failure, a great demonstration of why we do what we do matters. I wonder how much time, effort companies invest into BPSA in comparison to reservoir seal trap. You'll like that one. It's maybe a rhetorical question, but it's good.
But it is unfortunately the situation that they do spend about 100 times more work on geophysical anomalies and inversion and amplitude maps than understanding migration. That's the fact. But if you look at the results, this has been published not just by me, but also NPD. Hans Martin Wedding and his colleagues published 2-3 presentations at Force about this stuff. And then that detail is more in the EAGE website. But unfortunately, that is that companies identify even now big four-way closure on a beautiful 3D seismic far away from the kitchen, and they assume migration will go, but it's just not. So it's more like, behind the Utsira High migration shadow, 10 wells drilled in the last 15 years dry, one after each other, because companies, they just want to drill the high risk. Yes, but it's high volume. Maybe it works. Well, it's not. But in some cases, of course, it works. Like if you have a very good channel sense, like for example in the south now, this DNO discovery Otello, that's pretty far away from the active kitchen, but it's not the Jurassic, and it's a shallower carrier where there is migration from the deep basin 40-50 kilometers towards the northeast, and it works. But most of the time, the Jurassic, unfortunately, when it's in the migration shadow, it's not working. And then people don't spend enough time, or I would say they spend a lot of time on methods which are seismic, like amplitude anomalies and so on. But when somebody comes up with that, yeah, come on, but there's no migration, it's very high risk. They are, no, you might be wrong, and seismic is we trust, and yeah. So that's the case more likely, I would say.
Yeah.
If I go back to this one.
Yeah, some things never change. Good.
That's like,
And we have a question from Miss Samamkeli Jam. 3 questions. Rift basins with significant fault segmentation. How do you typically determine migration pathways? Second question, how do basin models differentiate between oil and gas windows when source rock properties vary laterally? Third, what are the best practices you take for modeling thermal maturation in complex areas like the North Sea, which is
yeah,
what
it's
we're talking
again,
about?
so I mean,
Okay.
yeah. So the first one, the faults. I mean, you have to have good maps. I mean, this, remember, on what you see on the slide is just a section and it's hand drawn, but real life, you have lots of faults, you have relay ramps, and so on. I mean, basically, you have to have a good map of your top source rock. If it's North Sea, then it's top Dropne or Mondal. If it's Brazil, I don't know, pre-salt, top rift, or Sirte Basin, Sirte Shale. But you have to have a good map. That's number one, the top. The base might be more difficult. Already in North Sea, it's difficult to map the base. Dropne, for example, it's not that easy. It's usually much easier at the top. But you can't assume constant thickness, because we know that on the highs it's thinner, basin it's thicker, but it's not as thick as the underlying one, for example. But when you have a good 3D map, when you have a real good understanding of the faults, you see the relay ramps, and relay ramps do play a role. So you can have migration into something where there is a good relay ramp working, and then it goes up. And then if you don't map it properly, you would say that it's not migration up. So that is, for example, how Johan Sverdrup was found, that it's a very good understanding from Lundin back in the days. They mapped very nicely the top basement and the top Jurassic, and they could understand that there is a big flat basement high where there could be migration. But definitely, it's good mapping and good understanding of the faults, and trying to understand when the faults become sealing. So that's the answer to the first one. The second, oil gas windows, of course, I mean, this is coming back to the calibration to good vitrinite reflectance. Use the newer one, the dogleg model from Burnham 19, and use different kinetics. You can use the simple kinetics, which work very well. The pepper and corn kinetics from 95 still work very well, I would say. Or use the newer ones, the multi-component ones. And then basically, the source of property is very laterally, yes, but they would, in most cases, they would vary because of the burial depth and the thickness. But if you look at TOC, if you change from like 5% in the basin center and 2% on the crest, it will not change your volume so much because the drainage areas are large. But if the maturity is immature in the close to the prospect, or it's mature, that has a very big importance. But I would say that the maturity plays more role than it's 2% or 3% or 5% TOC. And the last one is like, yeah, it's just good thermal calibration. I mean, you can always say that in most rift basins where you have the basin center very thick and more subsidence, it's usually colder than the flanking basement highs. Probably it's true in most rift basins that if you have a lot of wells on the basement high where there's a discovery, like Utsira High or Tampen Spur, you have probably a little bit higher thermal gradient and higher temperatures at the same depth. But that kind of difference is not that much. It's more like in the range of 5 to 10 Celsius. So it will be not that big effect, but don't be surprised if you drill in the basin center and at the same level, you have a little bit colder temperatures than in the basement high, because the basement highs will direct the heat up. But it will not be a huge effect. It's much more important when you have salt, for example. But there's a lot of good articles about how salt behaves and what is the effect. And then maybe some of the last.
Yeah,
maybe there's one from Øyvind, no?
Yeah, one more question popped up from Øyvind.
Yeah. How often do you get good mapped faults that you use in your modeling? Well, I think it's Øyvind's here. Well, it is that you have to do the mapping yourself. And I've been mapping a lot in Petra, the faults, fault planes, and fault polygons. that just have to be included. And yeah, but of course, if you have a 10,000 square kilometer basin model from Sirte Basin, for example, that is pretty difficult to get good quality fault polygons because it's probably no 3D seismic onshore, only 2D. So it varies a lot, which area you are. And then the last, maybe Stephen would, corner correction. Yes, corner correction is very, very important because if you just use the temperatures as a face value, they can be 10, 15 Celsius colder. Actually, the good thing is in Norway, every final well report should contain the temperature measurements. That's compulsory, and it's in open domain if it's older than 5 years, final well report. And then usually companies use the Horner correction in the final well reports. And you have to read that and you get the data out. And yes, it is. Rule of thumb can be varied, of course, which depth you are. But if you multiply, the first of all, you have to know what is your original temperature. If it's already Horner corrected, you can't correct it upwards because then you are overestimating it. But if it's a log-based temperature and the drilling mod is cooling it down, you can have very large differences. So the Horner can be 10-15% higher usually than the measured log based. So that's
Okay.
it.
Yep. Good. So I think we'll close the session now. Managed to get through all of the questions. So thanks again, Balazs. And we had a pretty good turnout, lots of interesting material, and especially a lot of references. So a lot of reading for everybody to do.